Hey, welcome everyone to our presentation on the principles of operation in a novel UV nitrate center that I'm really excited to share with you guys. My name is Kerry Caslow and I'm the Outdoor Water Monitoring Specialist for YSI. In this role, I assist a lot of customers with technical support needs and troubleshooting and also provide a lot of training on some of our water quality and level monitoring equipment. But today, outside of all that, I'm really excited to speak to you guys about our new NitraLED sensor and how it actually works. Before we get into that though, and talking about the new sensing technology, let's briefly discuss just a few of the reasons why people are even interested in monitoring for nitrate levels. So the first impact we'll talk about is eutrophication. So as nutrients enter a body of water, algae is going to grow, which feeds on these nutrients and also takes in oxygen. So the larger an algae bloom gets, the more that the sunlight is blocked, which also prevents the sun from reaching the aquatic plants, which keeps them from photosynthesizing and creating oxygen for the fish in the water. So as you can see, these two parts depleting the oxygen in the water causes dead zones, which really kills off fish. So dead zones can have huge economical impacts in addition to the environmental impacts. Fisheries and tourist industries are particularly sensitive to the health of the water. As a particularly large example of a dead zone, you can kind of think about the dead zone in the Gulf of Mexico. So the area of hypoxic bottom waters west of the Mississippi River can actually reach up to 23,000 square kilometers in the middle of the summer. Next, harmful algae blooms are another reason for monitoring for nutrients. Harmful algae blooms can be produced when excess nutrients again enter a body of water and particular types of algae start to grow. One toxin that is commonly sampled for is microcystin. Microcystin can cause significant health effects to humans and animals, causing anything from rashes to death depending on exposure and consumption levels. Harmful algae blooms are responsible for causing millions of dollars of lost revenue to the tourism industry, with about $4.1 million in just hotel losses in the 2019 HAB events along the Mississippi coast, and about $90 million lost in the 2018 Florida red tides. There can also be significant property value decreases up to over 20%, and extreme losses to fishery revenue due to the inability to gather healthy fish and shellfish, and millions of dollars, of course, in medical expenses, and of course it costs billions of dollars to remediate these areas. The third major reason that we monitor for nutrients is the health impact that nutrients can have on our drinking water. If there are excess nutrients in drinking water, significant health impacts can be seen. For example, if nutrients are commonly found in the drinking water that's used to prepare formula for babies, a syndrome called blue baby syndrome can develop. So to simplify this a little bit, it's basically when the body's red blood cells stop being able to intake oxygen, which leads to a blue skin appearance. And this doesn't just happen in babies, it can actually happen to adults who consume too much water that's nutrient rich as well. Other health effects of drinking water with excess nitrate are cancer, birth defects including neural tube defects, decreased blood pressure, increased heart rate, headaches, and more. The EPA has regulations on how much nitrate can be in public drinking water, but unfortunately not everyone has access to this type of water, so contamination of drinking water wells is a huge issue. So with that brief introduction to nitrate, let's now get into a new technology that we can use to monitor for this. So first we're going to discuss the principles of absorbance really quickly just to get everyone on the same page. Then we're going to cover the EXO NitraLED sensor itself and how it's the cool new sensor for your digital watershed. Diving deeper into the sensor, we'll talk about how the sensor corrects for the effects of sediment attenuation and absorption of light by natural organic matter. And then the goal by the end of this presentation is to make you completely aware of the science behind the sensor. So first we're going to do a quick little recap on the principles of absorbance. So this is going to be a really brief review because a lot of you are probably well aware of these equations, but they're pretty important, so just stick tight with me for a second. So first we have this piece of equipment in the water or in the lab, and on one side there's a light source that we kind of have represented by our light bulb here. That light is transmitted across a sample with a known path length, so that's kind of represented by our squiggly lines here. The light that makes it through the sample is captured by a photodiode on the other side, which is our last image here. What we have is a known incident light intensity at the start, and then the light captured by the photodiode is the transmitted light intensity. So this can be put into an equation known as Beer's law, which says that the absorbance is equal to the inverse log of the transmitted light intensity over the incident light intensity. So you can see the equation here on the screen. So as a really quick example, we see that there's no sediment or natural organic matter or really anything else that's absorbing light in the sample path here. So therefore, the incident light intensity is equal to the transmitted light intensity, which gives us an equation of absorbance equals inverse log of 1, which is equal to 0. So this means that there was 0 absorbance of light by anything else in the sample path. Next, we'll add in some stuff. So this stuff could be sediment particles, natural organic matter, or perhaps even nitrate. We'll pretend that the light intensity received by the photodiode is about half of that transmitted intensity by our light source. This leads to the equation absorbance equals inverse log of 1/2, which equals 0.3. So the next step with a lot of equipment would be to take this absorbance and then calculate a concentration using the Beer-Lambert law. But we're actually going to stop here because this is all that we need to know for the NitraLED sensor. The EXO NitraLED sensor was not designed to be a standalone sensor, but was designed to be a part of the EXO multi-parameter sonde and suite of sensors. The NitraLED sensor is the sensor in the middle of the slide here, and as you can see on the left, we can see the NitraLED sensor as part of a suite of sensors on the EXO sonde. So this suite could include other parameters like temperature, conductivity, turbidity, phycocyanin, chlorophyll, FDOM, and we also offer a lot more. On the right, we can see one of our colleagues deploying the EXO sonde in a protective tube for data collection. So now if you can kind of look at my camera, you can see that I'm holding up a NitraLED sensor so you can see how small this piece of equipment actually is. So if you know much about other nitrate monitoring devices, you know that this piece is significantly smaller than those are. So because of the small size and ability to be paired with additional sensors, the EXO package can be used to expand monitoring from a single site to a wide network for more thorough monitoring. And then by connecting the EXO to a data logger equipped with telemetry, you can have real-time data, which allows for the most real-time decision making. The EXO NitraLED sensor uses very powerful LED lights, one at 235 nanometers and one at 275 nanometers to measure nitrate and natural organic matter. The 10 millimeter sample path length allows for the wiper brush to pass through, but again, that number is not actually used in the calculation of the nitrate concentration, just kind of like I've alluded to previously and which we'll again discuss. On the other side of the path, so down here, is the UV enhanced photodiode that actually detects the light that has passed through the sample. In the body of the sensor then are the brains that store the calibration, the site-specific correction, and they also perform the absorbance and concentration measurements on the fly. The way that the NitraLED sensor determines a nitrate value is actually pretty simplistic. The total absorbance computed by the photodiode at the 235 nanometer wavelength is the sum of three things: the absorbance of nitrate, the absorbance of turbidity at 235 nanometers, and the absorbance of NOM at 235 nanometers. The equation shown here on the screen represents that. We know what the total absorbance at 235 nanometers is because that's what the sensor is actually measuring, but we don't know the effects of each of these components yet. So that's what we need to figure out. So in order to figure out the absorbance due solely to nitrate, we need to figure out what the absorbance due to turbidity and NOM are. So there's a separate equation for the 275 nanometer wavelength that's the sum of the absorbance due to turbidity and NOM at that wavelength, and then the absorbance due solely to turbidity will be based on the reading from the turbidity sensor. In order to get an accurate nitrate reading from the NitraLED sensor, you must have a turbidity sensor installed on the sonde, and we'll again talk about that in just a minute as well. So the first factor that the NitraLED sensor accounts for when trying to determine the nitrate concentration in the body of water is turbidity. So I'd like to mention that it's vital that we calibrate this turbidity sensor before performing any NitraLED calibration or site-specific correction. So to account for turbidity, we must use the data from the calibrated EXO turbidity sensor and relate the characteristics of different specimen of sediment to an absorbance. As you can see in the graph here, the varying sediment types at different concentrations have different absorbance values. For instance, the average sediment type and the sediment type that we programmed into the sensor by default is kaolin, which is the yellow line that you can see here. If the sediment type in your body of water was significantly different from K-LEDs, such as Elliott silt loam, you can see that there would be a large difference in accounting for the effects of turbidity. So you may be over or under correcting depending on your sediment type. So Elliott silt loam is the green line here. Using this example, we can see that at 60 FNU, our K-LED coefficient absorbance is approximately 0.2, but our Elliott silt loam absorbance is actually only about 0.1. So the specific sediment type is calibrated to by following the site-specific correction procedure, which requires you to calibrate in an unfiltered raw water sample and then a filtered water sample to compute that specific sediment linear regression equation. And we have an example of that coming up. In the site-specific correction process, there are 2 steps dedicated to computing the regression equation for the particular site you're interested in. In the first portion, the sensor is placed in a raw sample of water, as seen in the image on the right here. The sample needs to be continually stirred in order to get the most accurate turbidity value for this point. If any sediment starts to settle out, the turbidity value for the calibration of this upper point is actually going to be incorrect. So once this step has been completed, the upper point for computing the regression slope has been determined, and in this graph we can see that the red star is going to be our example. In the next step, the sample water is filtered through a 0.45 micron filter so that the sediment is completely removed. The turbidity level after this step should be less than 0.5 FNU, and if it's not, we recommend filtering the sample again through a smaller pore size filter, such as a 0.2 micron filter. This becomes your 0 point for the regression equation, as noted by the green star in our graph here. So the white line that we see going from the green star to the red star and continuing outward is now how we would determine the absorbance of light based on the level of turbidity in the water. So we're going to be correlating that turbidity level to an absorbance. As mentioned previously, the K-LED line is our default equation that we have programmed into the sensor. If your turbidity levels are continuously very low, such as maybe in a mountain stream, you may want to consider just using the default turbidity coefficients and only correcting for NOM during the site-specific correction procedure. As you can kind of see in the graph here at the low end, there's really very little difference in absorbance between most species below 20 FNU. So for these low-end turbidity applications, using our default coefficients may be the easiest option for you. But again, that's entirely the user's call. Once we know how to determine the effects of turbidity on the absorbance of light in the NitraLED sensor, we can rearrange the equations that we had at the beginning because now some of our unknowns are known. So please note in the examples on the previous slide that we were only looking at the chart at 235 nanometers. So these same types of regression equations are built for the 275 nanometer LED, but I chose not to show those in this presentation, but they do exist. So the resulting equations that we have now, we have solved for these items on the left, and we need to know these items on the right. So now on this slide, before we get too carried away with the equations that we see here, let me just quickly clarify what NOM is. So NOM is natural organic matter, which is a large mix of organic compounds like leaves and algae and plant and animal waste. A subset of that is a thing called dissolved organic matter. And then as a subset of that, we have what's called fluorescent dissolved organic matter, which is something that we actually have a sensor for. What I do want to point out here is that all FDOM is NOM, but not all NOM is FDOM. So now let's pop back into the equations here. So now since we have solved for the absorbance due to NOM at 275 in our second equation here, we now need to see how that relates to the absorbance of NOM at 235 nanometers. So once we figure out the relation between these two variables, we can solve for NOM at 235 nanometers and thus solve for the absorbance due to nitrate. As we can see in the example plot here, the absorbance of NOM changes at different wavelengths. So the correlation between the two is what we call the NOM coefficient, which is the proportion of the NOM at 235 to the NOM at 275. Since not all NOM is created equal, this coefficient can change, which is why the site-specific correction procedure allows a user to adjust the value as needed for the site. This step is performed in a filtered water sample because, again, all influences from turbidity need to be removed to account only for the interferences from NOM. So this is an automatically adjusted value in the software, but it can also be manually adjusted by the user as well. So once we know that coefficient, we can do some simple math to determine the absorbance due to NOM at 235 using the coefficient equation or slope that we just discussed. So in the equation here, we see that our absorbance from NOM at 275 multiplied by our NOM coefficient gives us the absorbance of NOM at 235. So going back to the original equations, we then adjust the equations based on the knowns and are able to input some numerical values, which leads to the end goal of having the absorbance value for nitrate. So it took a bit of time to get to that absorbance value for nitrate, but we still don't have a concentration for this value. So how then do we get our final answer? What we are then going to rely on is the 2-point calibration in pure nitrate standards that was actually done before any of this started to take place. So during the calibration procedure, we created a linear regression equation that allows us to relate the absorbance from the sensor to a nitrate value. An example of this regression is seen in the chart here. The sensor determines what the value of nitrate is based on the absorbance value that we found after those previous calibration steps. It's extremely important during the calibration and site-specific correction procedure and deployment that the sensor faces remain clean so that the most accurate readings can be made at all times, since we see that turbidity and NOM can have such a significant effect on the nitrate calculation. After the calibration and the site-specific correction steps have been performed, it's time to let the sensor actually do its job and collect some data. So the graph here is an example of how the NitraLED sensor compares to another sensor during a storm event. The turbidity, which is the red line, during this storm event reached approximately 375 FNU, which is actually a little bit higher than our recommended measurement range. This increased level of turbidity caused the sensor to overcorrect the nitrate data during the peak of the event, but as seen here, the other sensor also missed this portion of data, but that was due to fouling. So as the water receded, the EXO NitraLED data actually returned to normal functionality because the anti-fouling wiper kept those sensor faces clean enough to not warrant a site visit. Whereas this other sensor actually needed to be tended to, as you can see from this spiky erratic data right here. Zooming out to view the remainder of the data at this site, we can see that the storm event is right here. And you can also see additional comparisons to the other sensors. So as you can see, our NitraLED sensor, which is in blue here, was able to accurately measure ranges of nitrate from about 0 milligrams per liter up to about 20 milligrams per liter. So as you can see from this presentation, the computation of nitrate in the NitraLED sensor is pretty complex, but it's intended to provide the most accurate readings as part of a robust water monitoring system. So I just want to say thank you guys so much for your time. I'm happy to answer any questions that you may have, or you can reach out to myself or to our tech support team at any of the contact information that you see on the screen here. Thanks again.